Here's Richardson's adaptation.
Big whorls have little whorls, which feed on their velocity, and little whorls have lesser whorls, and so on to viscosity.
Richardson was the pioneer who invented mathematical weather forecasting in the 1920s. He intuitively understood the mathematical complexities involved, which we now know include chaos. He also realized that practical forecasting would require massive amounts of calculation. The mathematical historian A.J. Cree has described why Richardson was ahead of his time.
Richardson made an attempt to calculate solutions by using numerical methods. He actually visualized an orchestra of human computers carrying out the vast numbers of calculations under the baton of a mathematician. His real need was a powerful computer.
A half-century after Poincaré's work, and 20 years after Richardson's vision of a mathematical orchestra, computers appeared in the 1940s. People started calculating values for equations rather than using algebraic techniques to solve them. Then the inevitable happened. Chaotic behavior turned up in the output. Edward Lorenz, a meteorologist with a background in mathematics, first noticed apparently nonsensical numbers coming out of his machine, and he realized their significance. The year was 1963, and that date marks the beginning of what has been called experimental mathematics. Here, mathematicians use a computer to calculate results over and over, looking for patterns in the output, just as a scientist looks at the results of an experiment. This is very different from the traditional methods of proofs and theorems used by past generations of mathematicians. David Campbell explains.
The term experimental mathematics has been coined to describe computer-based investigations into problems inaccessible to analytic methods. Rather than simply confirming quantitatively results already anticipated by qualitative analysis, experimental mathematics uses the computer to generate qualitative insight where none has existed before.
Traditional mathematicians argue that experimental math cannot prove that the insights from its calculations are universally valid. These traditionalists insist that proper mathematical proof is still necessary, and in fact experimental mathematicians usually try to provide such a formal proof. But the new mathematics is driven by experimental results, and experimental mathematics itself is shaped largely by the needs of the scientists who are investigating novel phenomena. In other words, the new mathematics and the new scientific knowledge have developed together. It's just like the invention of calculus by Isaac Newton, who needed a new mathematical language to express his new science of mechanics. Edward Lorenz continued to work on the mathematics of chaos beyond 1963, but it was a decade before others realized the significance of his discovery. Robert May, as we've seen, was one of the first, publishing his work in 1973. Another was physicist Mitchell Feigenbaum. Feigenbaum was interested in complex phenomena, especially turbulence, and he decided that the logistic equation could serve as a simple but useful model. The bifurcations leading to chaos nicely represent the onset of turbulence, so Feigenbaum began to investigate the series of bifurcations using a hand-held calculator. It soon became apparent that the transition to chaos progresses at a rate that can be described by a particular number, approximately 4 2/3. Soon Feigenbaum and other scientists realized that many other systems, from a variety of fields such as physics, meteorology, biology, medicine, and economics, also were characterized by the same number. Feigenbaum had discovered a mathematical constant that describes the transition to chaos in a large class of systems. This constant would become a fixture in mathematics, just like pi, the ratio of the circle's circumference to its diameter. Now known as Feigenbaum's constant, This new mathematical tool was a profoundly important advance. Ironically, Feigenbaum had made his discovery not with a huge state-of-the-art computer, but with a simple handheld calculator and a state-of-the-art brain.